Hello and welcome to today's presentation, which covers the basics of chemistry and the periodic table. It's called The Power in Your Palms because the periodic table can be super helpful if you know how to read it. And I'll be going over some of the basics that you need to know about the periodic table in order to be successful in your chemistry journey. My name is Trinity Joshua. I'm one of the science tutors here at Lone Star College University Park, and let's begin. First off, there is a lot of information in the periodic table. It's taken many years for people to gather all the information and store it in a way for you to read. And so it is here for you to use. It is powerful. Like, you don't need to memorize these things. You don't need to memorize a whole lot. All you need to do is remember how to read the table, and it can help you along. So first off, let's begin with some of the basics of how to read the periodic table and some of the basic information that's provided to you here on the periodic table. So first off is how to read each element square. We're going to go top to bottom. The first one is the atomic number. That is the number of electrons or protons, and I put in parentheses while neutral, because obviously chemistry is all about the swapping of electrons. It can get complicated, but the atomic number tells you the number of electrons and the number of protons that the atom has when it's neutral. And remember, in a neutral atom, the number of electrons is equal to the number of protons. Below that is the element symbol. This symbol is just shorthand for the element. So it comes in handy when making equations and such. Most of the time, the element symbol will be a letter or two from the actual element name, but sometimes the element symbol doesn't match the name. So make sure you have your periodic table handy so that you can match the element symbol to what the element is. The element name is below, and beneath the element name is the atomic weight. And the atomic weight is also known as the atomic or molar mass. This is because the atomic weight is equal to the number of protons plus the number of neutrons. And this also is equal to the grams per mole for that element. So if we look at a basic periodic table, it will show you this one shows you the atomic number, so you can know how many electrons and how many protons each of these elements has. For example, if you look at fluoride all the way to the right, its atomic number is 9, which means that it has 9 electrons and also has 9 protons when the atom is neutral. This periodic table doesn't show you the atomic weight, but most of them do. And the atomic weight isn't something you have to calculate. That's something I really want to emphasize. I see that a lot while tutoring, that some people will try to figure out how to calculate the atomic mass, but it's already given to you here in the periodic table. So that's something that saves you some time and saves you some thought energy, right? A quick note, the periodic table is organized by columns, which are called groups, and by periods, which are the rows. Another important function of the periodic table is that they're split into different sections. These are different sections because the elements are similar in traits and how they act when reacting. That's why we section them together. And most of the sections are based off of they're based off columns, right? So they're going up and down. Going from left to right is alkali metals and alkaline earth metals, transition metals, then halogens, and then noble gases. And at the bottom are some extra metals that we don't really use a whole lot, but there are lanthanide metals and actinide metals. And each of these sections acts similarly. Most periodic tables have it sectioned out like this, where each section will have its own color. So going back to this table, the alkali metals have one color, the alkaline earth has another, and etc. And again, it is important to note that each of these are different sections because they act similarly. And these sections are often used in word problems given by professors. So just knowing that group 18 is known as noble gases, group 17 is known as halogens, and etc. will be helpful for when you get those problems on a test. Or you can just get a periodic table like this one that already tells you, so that way you don't have to memorize it, right? This here is the periodic table I personally have, because it gives you so much information at once, right? It can be a little bit overwhelming, but it is super helpful for when you, as long as you know how to read it, right? So as you can see, it gives you the different colors based off the different groups. So you know what color the alkali metals are, you know what color the alkali earths are, you know what colors the halogens are, etc. This table is also helpful because it gives you the what state of matter these elements are at room temperature. Most of them are solid at room temperature, and there's 11 that are gas at room temperature, and only 2 that are liquid at room temperature. This table has them in different colors, right? So gas is blue, liquid is red, solid sort of bold black color is when it's solid at room temperature, and the sort of see-through white one is synthetic, meaning that it's made and isn't around long enough for us to know what state it would be at room temperature. Not all periodic tables show the states of matter, but it is helpful if you do have one that gives you this information in case you get one of those questions on the test. So the next thing that we go on is electrons on the periodic table. Now, electrons are super important. The movement of electrons is what causes electricity for physics students, but it is what causes chemical reactions for the rest of us that allows life to happen. So the atomic number, like I said, is the number of electrons or the number of protons while the element is neutral. This means that the normal version of the element will have that many electrons, right? So for example, this is a hydrogen. Hydrogen will normally only have 1 electron and 1 proton, right? Because remember, when an element is neutral, that means it has the same number of electrons as the number of protons. So the 1 both stands for the number of electrons that the hydrogen has and the number of protons that the hydrogen has. And the other important number on this page that talks about electrons is the atomic weight, because the atomic weight tells you the number of protons plus the number of neutrons. Protons have a weight of about 1, and neutrons have the remaining weight, basically. Electrons are so light that we don't really consider them in regards to weight. So for this one, for this hydrogen, there's 1.008 is the atomic weight, which is the number of protons and the number of neutrons. Hydrogen itself doesn't have a neutron, so it is just 1.008. But if we were to look at something else, like let's choose oxygen. Oxygen has an atomic number of 8 and an atomic mass of 16. That means there's 8 protons, and 16 minus 8 means that there's 8 neutrons in that atom. Does that make sense? It'll get easier the more you do it, but for now, let's move on to valence electrons. These come in super handy. They're very important as you move on in chemistry. The valence electrons are the number of electrons in the outermost shell. Only the electrons in the outermost shell are the ones that form and break bonds. And lucky for us, we don't have to memorize it per element. You can just see it based off of what group number it's in, right? So for group 1, they only have 1 valence electron. For group 2, they have 2 valence electrons. We skip the transition metals, which I'll explain later why. And then we'll move on to group 13, which only has 3 valence electrons, and etc. 4, 5, 6, 7, and 8. Noble gases have a full octet, meaning they have 8 electrons in their shell, meaning that their outer shell is full, right? Because the shell is full when there's 8 electrons in there. So these top numbers tell you any element in those columns have 8 or 7 or 6 or 5 or 4 or 3 or 2 or 1, however many in the column, it has that many valence electrons. Now, transition metals are the oddballs. We'll get into it later, but these guys have a way of putting electrons into inner shells. So they can react differently. They can break the octet rule sometimes, even like they're just their own beast. So for now, let's not worry about transition metals too much. But if we look at transition metals a little bit, you can see that they can form more than one ion. So most elements, if you come back to this one, right, most elements can only give as many electrons as are in its outermost shell, right? It can only react with those valence electrons. Transition metals are the weird ones because they can react with electrons in their inner shells and their d orbitals, which we'll go over later. But for now, remember that transition metals can form more than one ion due to their d orbitals. So these are some examples here. Iron can either give 2 electrons or give 3 electrons. Copper can give 1 or 2. Manganese can give 2 or even 1. So these are just examples of those transition metals, those guys in the middle. They can do all sorts of stuff. So just be aware that they can change. And because they can change, when we start reacting with these metals, we have to specify, okay, what charge is it doing today? Because it could be multiple charges. So speaking of orbitals, orbital information is also given on the periodic table. If you remember, orbitals are a fancy way of saying where the electrons are around the element when it's just chilling, right? When it's not doing anything. So at the top is the s orbital, the red orbital. This is the first ring, the first orbital that the atom will fill when it's gaining electrons, right? The P's, the yellows, are the next set. So there's P-1, P0, and P1, or as I learned, PX, PY, and PZ. So then they have another set of 3 electrons that they can, not electrons, 3 orbitals that they can fill with electrons. And then it moves on to d orbitals, which they can fill, and then moves on to f orbitals, which they can fill. If you see in this right-hand corner, it'll show you the order in which they fill it, right? The elements want to fill up the inner shells before they move out to making outer shells. So if you look, the S's will be filled first, and then the 2 S's, and then it'll go to 2p6 and 3s2, and etc. So just having this thing in the corner of your periodic table will help you when you start getting into those upper courses or those chapters where they start talking about how to fill orbitals. But for now, just remember the basics. That S is the smallest orbital, P is a little bit further out, D is a little bit further out, and F is a little bit further out than that. And it'll fill these going from top to bottom. So on the periodic table, it will actually give you this information. It'll tell you what orbitals each of these elements has. If you look at the top, you can see that S block or elements are the elements that are orange in this one. P block are the ones that are pink. D block are the ones that are like the sort of light blue color, and F block are the ones that are the darker blue color. Sorry, I didn't mean to do that. And it fills it in order, just like this last page, where in the corner it will show you that it fills it in a particular order. It will do that forever. So you can literally just come over to this table and know what orbitals are present in a molecule. So for example, if we chose, let's choose fluoride, right? So fluoride, you can't really see my cursor, but fluoride is up at the top right corner. It's the second pink block from the right at the very top. So if we were to count, we'd see 1s, right? Then it fills up the 2 S's. And after the 2 S's filled, it'll go to the 2 P's. And after the 2p is filled, it'll fill it up right to where the element is. In our case, fluoride will be 2p5, meaning that there's 5 electrons in the p orbital. if we were to choose an element that is further down, you would literally just read it from left to right. So it would go from 1s, 2s, 2p, 3s, 3p, 4s. Transition metals are weird because they'll then put in electrons into their Ds, but of the third shell, if that makes sense. So the ones, the numbers, the 1, 2, 3, 4, 5, 6 is the shell, and the S and the D and the P and the F is the positioning in the shell. So like where in the shell it goes. Once you get down to 4s, these transition metals in the middle get weird because they'll start putting stuff in the inner shell, in the 3 shell instead of in the 4 shell. So down here you end up getting 4s, 3d, 4p, and they'll go straight back to 4p, and they'll go back to 5s and continue on with all the other ones. But then they'll start stuffing it back into the 4 shells again in the D. And it'll just continue on in that matter. It gets a little weird with these bottom ones again because transition metals, they can do that. They can put electrons into their previous shell, but for the most part, they will follow that simple pattern of, sorry, I keep doing that. They will follow the simple pattern of putting electrons in order. First the S's and then the P's, and going in numerical order too. So 1s first, then 2s and 2p, and 3s and 3p, and etc. And so this is really just a basic summary. You will be able to study this further with your professor in your textbook, so no worries if it's a little confusing now. But I'm hoping that this will give you a bit like of a heads up so that when you do see it, you can understand that all this information is still available to you on the periodic table. So yes, when you learn about orbitals in class, it can seem a little scary because there's so much information, right? I mean, there's lots of information on the periodic table, and back here you have to learn about the shapes of orbitals and all that jazz. But it's okay because once you learn about this in that chapter, you can then know how to read the periodic table, so you don't have to memorize the orbitals. You can just go off of the periodic table. This is just a basic understanding of how this works and a basic understanding of electrons and how to read the different elements on the periodic table. And you will study these further, but I hope this helps you as you continue on. So let's move on to the trends of the periodic table. So periodic table trends are super important because they give you hints, again, of how similar elements react to each other and how the table is organized to show you the different characteristics of each element. Questions about these trends tend to appear in the first chemistries you take, so general chemistry or inorganic chemistry, but you will also have questions that involve these trends in organic chemistry. So it is important to understand, at least just from a basic definition, understand these trends. If you don't understand the orbitals, or that's okay, you'll have time to understand this, but understanding how to get the electron number from the table and understanding periodic table trends are some of the most fundamental things you need to know. The great thing though is that trends tend to relate to each other on the periodic table. It means that they tend to go in similar directions. So if you remember like 2, you should be able to remember you'll be able to get the rest too because they're similar, they relate to each other. So let's move on to the first and honestly, in my opinion, the most important trend, and that is electronegativity. So electronegativity is a tendency the atom has to attract electrons. Basically, how strongly does it pull at electrons? Fluorine is in red here, is the most electronegative atom, while francium at the very bottom left, which is blue, is the least electronegative. And the arrow shows you in the direction, shows you the direction that electronegativity grows. So as you head to the right and as you head upward, atoms will become more electronegative. Does that make sense? And vice versa, as you head to the left and as you head down, it'll become less electronegative. The closer you are to fluorine, the stronger you are at pulling electrons. Now, electronegativity is often mixed up with electron affinity. Electron affinity is how much energy is released from an atom when it accepts an electron. So how much energy the electron must give in order to take an electron. A large energy release means that the atom, quote, wants to have the electron. Does that make sense? So if, so fluorine will have a high electron affinity, meaning that it will drop a lot of energy for the sake of getting an electron, while francium won't. Francium won't give off that much energy because they don't really want the electron, right? They're not very electronegative, so consequently, their electron affinity will also be low. So electron affinity goes in the same direction as electronegativity. If you understand it like that, like almost how much does the element want to pay for the electron, like how badly does it want it, it will help you remember the trend, that trend goes in the same direction as electronegativity. So fluorine will pay the most energy. It will give off the most energy to accept the electron, while francium will give off the least energy because it doesn't really want it. The next one, which sort of goes hand in hand with electronegativity, is ionization energy. So sort of like electron affinity, where it's how much an atom will pay to get an electron. Ionization energy is how much energy is required to pull the electron back off the element. Does that make sense? So ionization energy is the energy required to remove the first electron from the atom. You can also move on to find out the ionization energy of the second or the third, or et cetera. But most of the time when we're looking at ionization energy, it's talking about the first electron. So does it make sense that something that is very electronegative would also require a lot of energy to ionize, right? So ionization energy is going in the same direction. It's the same trend as electronegativity. So fluorine is super electronegative, right? It strongly pulls electrons. It also has a high electron affinity, right? It will pay a lot of energy to get the electron. And so in the same way, the fluorine will not want to give up an electron. So it will require a whole lot of energy in order to pull that electron off of it. So fluorine will also have a high ionization energy. So ionization, electronegativity, and electron affinity also to go hand in hand if you think about it that way. Electronegativity is how strongly it pulls. Electron affinity is how willing is it to get an electron, right? So those two go hand in hand. And then ionization energy goes hand in hand too, because it's how hard is it to get back the electron. All right, so moving on to the next one is atomic radius. The atomic radius is the size of the atom when it is neutral. It goes in the opposite direction of electronegativity. So it will actually increase the more left and the more down you go. So it goes in the opposite direction of the other ones we've learned. It goes in the opposite direction of electronegativity and ionization. And it can sort of make sense why, right? The more electronegative the atom is, the stronger it pulls electrons to itself, right? And if it's pulling strongly to itself, then it's holding it close to its chest, which means that it's like a smaller radius, it's a smaller ball. Does that make sense? So the more electronegative the atom is, the closer to itself the atom holds its electrons, which means that its radius is really small, which means fluorine is like one of the smallest atoms, right? Versus francium is super big because it doesn't really care. It's not really holding on to its electrons super tight. It can let go of it really easily. It's like an arm's length away. So atomic radius goes in the opposite direction as electronegativity and ionization energy. And just remembering that electronegativity is how strongly the atom pulls electrons, and that the stronger you pull electrons, the smaller you'll be. It'll help you understand atomic radius, because then you could just think, oh, if something is really electronegative, it is probably also going to be pretty small. Ionic radius, it goes in the same direction with atomic radius, because ionic radius is the size of the atom when it's an ion. Like I said, it goes hand in hand with atomic radius. If something is large as a neutral atom, it will still probably be big after as an ion, um, but it's not used as often. Ionic radius isn't used as often as atomic radius. Atomic radius is honestly the real one you need to focus on. Ionic radius will most of the time be given to you like in a chart or a table that shows you a periodic table that shows you the numbers. Just know that ionic radius is there. It is an important trend, and it goes in the same direction as atomic radius. All right, so metallic character. Metallic character is how easily the atom can lose electrons, and thus how easily it can conduct electricity. So I won't get into physics too much, but does it make sense that something that is electronegative, right? Something that holds on to electrons really tightly won't be very good at conducting electricity and won't be very metallic, because metallic character is how easily the atom can lose electrons. So electricity is the flow of electrons from one part of the circuit or one atom to another atom. If something is electronegative, it's not going to lose electrons, so it's not going to be able to flow electrons, so it's not going to be able to conduct electricity, right? Which means it's not going to be metallic. Versus something that can easily lose electrons, it will be metallic because it can keep shuffling electrons along the circuit instead of grabbing onto it and holding onto it. So metallic character goes in the opposite direction of electronegativity, because the more electronegative something is, the more non-metallic it is. If something isn't very electronegative, it'll probably be more metallic, especially if you look at this chart. So metallic character increases in the same direction as atomic radius. And non-metallic character is the opposite, right? So it will increase with how electronegative it is. And again, all these trends and traits will get easier the more you see them and the more you use them, but it's just good to know now how all these things relate together. And so this is like a summary of all that you've learned. If I can emphasize one trend, I would say electronegativity is the most important trend. If you get an understanding of electronegativity, you can logically work out what the other ones are, right? So electronegativity increases as you go to the right and as you go up. And the more electronegative it is, the more energy it will give off to get an electron, right? So that means electron affinity increases in the same direction, and ionization energy increases in the same direction, because that means the more electronegative something is, the more energy will be required to pull an electron off. And moving on to atomic radius, if an element is electronegative, it will be small because it'll be holding things close together. So atomic radius increases to the left and as you go down. And something that goes hand in hand with atomic radius is ionic radius, which isn't on this chart, but metallic character also increases as the atomic radius increases. And so this is just a handy chart. You can find charts like this on the internet that can remind you. Personally, I have my periodic table, and I actually wrote these arrows down on the periodic table so that whenever I looked at the periodic table, I knew what trends were there and what they were doing. And that's it, guys. I mean, that's a general understanding of the periodic table. You'll practice this as you go on in your chemistry courses. It'll start becoming easier to understand. You'll start going to memory, but just understand that the periodic table is actually super helpful. You don't need it. There's some things you don't need to calculate, some things you don't need to Google. It's literally right there for you, as long as you can practice looking at the periodic table and understanding the information on it. It took over 2 centuries to gather and put all this chemical information together for you. Like, it's in the palm of your hands. All you gotta do now is learn and practice how to read it and understand it, and you'll do great. One of the helpful resources I would love to suggest to you is ptable.com. This periodic table is honestly my favorite because it can show you all the information that you ever need. Um, like for example, in this screenshot, this is like a basic periodic table that you can find printed out, but you can also click on other things, right? On other tabs, and it will show you the electron number or the valence electron number or the energy levels, or you can see here on the left, it'll show you the electronegativity, the boiling point, the melting point. It gives you all the information you'll ever need. So I would keep this table bookmarked so that you can have all the information in one place if you need it. But again, I suggest you print out your own copy of the periodic table to have with you, especially since for most tests, professors don't allow you to have the internet open. If you print out the periodic table and just keep on the table like some of these trends or reminders of these trends, it'll help you out a lot as you continue on in your chemistry journey. So thank you so much for listening. I hope this helped you understand the periodic table a little bit more. If you need any help going over this, please reach out to your professors, but also feel free to reach out to us tutors in the Science Hotspot. We're located in the Center for Science and Innovation building, and we'll have hours posted and in the Science Hotspot. So please feel free to reach out to us if you need anything. There's also online tutoring provided to you through Lone Star College University Park. We pay for it. So if you need any online tutoring, we can also provide you information with how to connect to that free resource. So thank you guys so much for joining us today, and have a great rest of your day.